All right, so today's deep dive
Uh-huh.
is into something pretty wild.
Okay.
Quantum computers.
All right.
Specifically, Google's new Willow processor.
Okay.
Have you heard about this?
Yeah, I've been following that.
It's,
Pretty remarkable stuff.
yeah, so it solved a problem in under 5 minutes that would have taken a classical computer
Right.
10 septillion years
It's really
of,
it's really interesting how Willow achieved this.
Yeah.
It's not just about the speed.
right.
It's about tackling a specific problem that demonstrates that
Okay.
quantum supremacy.
Okay.
That point where quantum computers can outperform even the most powerful
Okay.
classical computers we have.
So before we get too far,
Sure.
let's back up a bit.
Yeah.
For anyone listening who's not a quantum physicist,
Right.
can you just break down the basics
Yeah.
of what a quantum computer is?
Yeah, you're right. It
Okay.
can get complicated very quickly.
Yeah.
But at their core, quantum computers use these things called qubits. And qubits are kind of like the bits in our regular computers,
Yeah.
but with a quantum twist.
Okay.
So while a bit can be either a 0 or a 1,
Right?
a qubit can be in this state called superposition,
Okay.
meaning it's both 0 and 1 at the same time.
All right. Now I'm feeling a little lost.
Yeah.
Superposition.
Superposition, yeah.
Is that where the whole quantum weirdness
It
comes
seems
in?
that's where it all comes in.
Okay.
It's a mind-bending concept that comes from quantum mechanics.
Okay.
Think of it like a spinning coin.
Okay.
Until it lands, it's technically both heads and tails simultaneously.
Uh-huh.
That's what a qubit is doing in superposition.
Okay, I think I'm following. So
Yeah.
how does that make a quantum computer
Right.
so much faster than a...
Yeah, well, it's not just superposition.
Okay.
There's also this concept called entanglement,
Okay.
where two qubits are linked in a way that they influence each other instantaneously,
Whoa.
even if they're physically far apart.
Okay.
So imagine two of those spinning coins. If one lands on heads, the other instantly flips to tails, no matter how far apart they are.
No way.
That's entanglement.
Whoa, okay.
Yeah.
So with these entangled qubits,
No.
what kind of problem was Willow tackling?
Right. So,
You mentioned a benchmark before?
yeah, this specific task was called a random distribution benchmark.
Okay.
Imagine you have a giant box
Okay.
filled with 1 billion marbles,
A billion. Okay.
all shaken up.
Got it.
The benchmark challenges the computer to predict the exact arrangement of those marbles
Oh, wow.
after they settle.
Okay.
It's a problem with an insane number of possible outcomes,
Right.
and it's practically impossible for a classical computer to solve
Yeah.
in any reasonable time frame.
Okay. And Willow just did it
Yep,
in under 5 minutes.
in under 5 minutes.
Wow.
And this is where its unique architecture comes in.
Okay.
So Willow uses a specific type of superconducting transmon qubit that Google's been developing.
Uh-huh.
And these qubits are arranged in a two-dimensional grid. And Google's team has made significant strides in improving their stability and coherence,
Okay.
which basically means they can stay in their quantum state for longer, allowing for
Got it.
more complex calculations.
So it's not just about throwing more qubits at the problem.
Exactly.
It's about...
It's about how those qubits are designed and connected.
Yeah, okay.
And that's why this achievement is so significant.
Okay.
It shows that Google is making real progress in building practical,
Right.
large-scale quantum computers.
Okay, so this quantum supremacy thing,
Yeah.
didn't Google claim that a few years ago too?
They did.
Yeah.
But it was with a much smaller quantum chip.
Okay.
And there was some debate about whether a classical computer could have eventually solved it,
Right.
just very, very slowly.
Right.
Willow's performance is on another level entirely.
Yeah.
This time, it convincingly outperformed any classical computer.
It's impressive.
Yeah.
But before we get into all the amazing potential of quantum computing, I know some people listening might be wondering, like,
Yeah.
how do you even build a computer
Right.
that relies on these weird quantum principles?
Yeah.
Isn't it all incredibly delicate and prone to errors?
Absolutely.
Yeah.
One of the biggest challenges in quantum computing is dealing with those errors,
Okay.
because these qubits are incredibly sensitive to any kind of environmental interference.
Oh, really?
Yeah, so temperature changes, vibrations, even stray electromagnetic fields
Wow.
can knock them out of their delicate quantum states.
So it's not like we can just stick a quantum chip in our laptops anytime soon.
Not quite.
Okay.
It's a major engineering challenge.
Right.
Researchers are working on incredibly sophisticated error correction techniques,
Oh, wow.
essentially building quantum spell checkers that constantly monitor the qubits and correct any errors that pop up.
Wow. Quantum spell checkers.
Yeah.
That's That's a lot to process.
Is.
I think we need to take a closer look at these challenges
I agree.
and what they mean for the future of quantum computing.
Yeah.
And while we're at it,
Yeah.
maybe we should address some of the more
Sure.
exotic ideas that are floating around.
Right.
Like the notion that Willow might be tapping into parallel universes for his computational power.
Okay.
Now, that's what I call a cliffhanger.
Yeah.
So let's take a quick pause here,
Okay.
and we'll be back in a flash to tackle those mind-bending possibilities.
Sounds good.
So we've established that quantum computers are super complex,
Yeah.
super delicate,
Right.
and potentially super powerful.
Huh.
But I gotta admit,
Yeah.
those quantum spell checkers you mentioned
Right.
really have me intrigued.
Yeah.
How do you even begin to correct errors
Right.
in a system that's based on uncertainty and probability?
It's a fascinating field, and it's where a lot of the cutting-edge research is happening right now.
Okay.
One approach is to use redundancy.
Okay.
Instead of relying on a single qubit to store information,
Right.
you create multiple copies,
Okay.
kind of like having backups. So then if one qubit gets knocked out of whack,
Right.
you can use the other copies to figure out what the original state should been
Okay.
and correct the error.
So it's like a quantum version of
Upgraded.
two heads are better than one.
It is, yeah.
Okay.
But it's not just about copying qubits.
Okay.
There are also techniques that use complex algorithms to detect and correct errors
like that.
by manipulating the entangled states of multiple qubits.
Right.
It's a bit like solving a puzzle.
Oh,
You have to figure out which pieces are out of place
got it.
and then carefully rearrange them to get back to the correct configuration.
That sounds incredibly complex.
It is, yeah.
I can only imagine the kind of brain power it takes
Right.
to develop these error correction methods.
It definitely attracts some of the brightest minds
Yeah.
in physics and computer science.
Right.
And the progress they're making is remarkable.
Okay.
With each generation of quantum computers,
Yeah.
we're seeing significant improvements in error rates
Yeah.
and coherence times,
Okay.
which means we're getting closer to building machines that can reliably perform long and complex calculations.
So let's assume for a moment that we do crack the code
Yeah.
on error correction.
Right.
And we build these large-scale,
Mhm.
stable quantum computers.
Yeah.
What kind of real-world impact
Right.
would they have?
Yeah. The potential applications are vast.
Okay.
They span across numerous fields.
Like what?
One area where quantum computers are expected to make a huge difference
Okay.
is in drug discovery and material science.
Okay.
So imagine being able to simulate the interactions of molecules at the quantum level,
Okay.
allowing you to design new drugs with incredible precision
Wow.
and target specific diseases with unprecedented effectiveness.
So we're talking about potentially curing diseases
It's certainly
that are currently incurable.
within the realm of possibility.
Wow.
And it's not just about drugs.
Okay.
Quantum computers could also revolutionize material science by allowing us to design new materials with properties that we can only dream of today.
Go ahead.
Stronger, lighter, more efficient materials
Wow.
that could transform everything from aerospace and transportation
Right.
to energy production and electronics.
It sounds like we're talking about a technological revolution
On
on par with the invention of the internet
a fair comparison. Yeah.
or the development of the microchip.
Absolutely.
Wow.
And let's not forget about cryptography.
Okay.
You know, the security of our online communications
Really?
relies on these complex mathematical problems
Right.
that are difficult for classical computers to solve.
Right.
But quantum computers could potentially break these codes,
Really?
which means we'll need to develop entirely new encryption methods
Wow.
to keep our data secure.
That's a bit unsettling, to be honest.
It is, yeah.
It seems like every technological leap forward
Yeah,
comes with its own set of challenges
it's true.
and potential downsides.
But it's also what makes this field so exciting. We're not just developing new tools.
Yeah.
We're grappling with fundamental questions
Right.
about the nature of computation,
Oh.
the limits of our current understanding of physics,
Okay.
and the ethical implications of wielding such immense computational power.
Okay, so we've covered the challenges,
Right?
the potential applications,
Uh-huh.
and even touched on the ethical considerations.
Mm-hmm.
But we can't wrap up this deep dive
Right.
without addressing the elephant in the room.
Sure.
Or should I say the parallel universe
Okay.
in the quantum computer.
Right.
What's the deal with this idea that Willow might be tapping into other dimensions
Yes.
to do its calculations?
The multiverse hypothesis.
Okay.
It's a fascinating idea.
Yeah.
And it's certainly captured the imaginations of many people.
For sure.
The basic premise is that every quantum measurement,
Okay.
every time a qubit collapses from a superposition of states
Right.
into a definite 0 or 1,
Okay.
creates a split in the universe, branching off into a new parallel reality
Okay.
where the opposite outcome occurred.
So you're saying that there might be an infinite number of universes out there, each representing a different set of quantum choices.
Yeah.
And that Willow is somehow accessing the computational power
That's the idea.
of these other universes to solve problems faster.
Though I should emphasize that it's a highly speculative idea.
Okay.
There's currently no scientific evidence
Okay.
to support the existence of a multiverse.
Right.
And even if it does exist,
Yeah.
we have no idea how we might interact with it or harness its computational power.
It sounds like we've ventured into the realm of science fiction here.
A little bit, yeah.
But even if the multiverse is just a theoretical possibility,
Right.
it does make you wonder about the truly mind-boggling implication
It does.
of quantum computing.
It certainly does.
Yeah.
And while the multiverse is a fascinating topic to ponder,
Sure.
I think it's important to remember that we're still in the very early stages.
Okay, of understanding quantum computing itself.
Right.
You know, we've made incredible progress,
Yeah.
but we still have a long way to go
Okay.
before we can even begin to grasp the full potential of this technology.
I think that's a great point to end on.
Yeah.
We've covered a lot of ground today.
We have.
From the basics of quantum computing
Right.
to the mind-bending possibilities of the multiverse.
Uh-huh.
But before we wrap up entirely,
Sure.
I think it would be helpful to summarize what we've learned
Okay.
and leave our listeners with some final thoughts to chew on.
I agree. Let's recap what we've explored
Yeah.
in our deep dive into the world of quantum computing.
So we started this deep dive by unpacking the fundamentals
Uh-huh.
of quantum computing. These incredible machines
Yeah.
utilize these things called qubits, which can exist in a state of superposition,
Yeah.
meaning they can be both
It can
a 0 and a 1 simultaneously.
be both at the same time.
It's pretty crazy.
It is, yeah. We also talked about entanglement.
Right.
That's the spooky phenomena where two qubits become linked.
Yeah, if you change the state of one,
Right.
the other instantly changes too, no matter how far apart they are.
It's wild.
It is.
These principles of superposition and entanglement give quantum computers their incredible power,
Yeah.
allowing them to explore a vast number of possibilities
At once.
at once.
Yeah.
And of course, we had to discuss Google's Willow processor.
Right.
This 105 qubit beast
Yeah.
just shattered a computational benchmark.
Yeah,
Would have taken a classical computer
An unfathomable amount of time.
an unfathomable amount of time to solve.
Yeah.
It did it in under 5 minutes.
Under 5 minutes.
This accomplishment
Yeah.
is a major step towards
Quantum supremacy.
quantum supremacy.
Yeah, that's the point where quantum computers surpass the capabilities
Wow.
of even the most powerful classical computers we have today.
But we didn't shy away from the challenges either.
Right. We talked about how quantum computers are incredibly sensitive to errors.
Yeah.
Things like temperature fluctuations or stray electromagnetic fields
Right.
can disrupt those delicate quantum states.
Yeah, so we need those quantum spell checkers.
Yeah, you need those error correction techniques
Yeah.
that are essential for making quantum computing reliable and scalable.
Speaking of scalability, that's another big hurdle.
It is.
Right now, we're working with systems
Yeah.
that have a few hundred qubits at most
At most, yeah.
to tackle really complex problems.
Right.
We'll need quantum computers
Millions of qubits.
with millions of qubits working together harmoniously
Living together, yeah.
despite these challenges.
Yeah.
The potential applications of quantum computing are absolutely mind-blowing.
Mind-blowing.
We're talking about breakthroughs in medicine,
Uh-huh.
material science,
Artificial intelligence.
artificial intelligence,
Photography.
cryptography. Wow.
It really does span numerous fields.
Imagine designing life-saving drugs in a fraction of the time,
Right.
or creating new materials with properties we can only dream of today.
Exactly.
Quantum computers could truly revolutionize our world.
They could, yeah.
And then there's the multiverse hypothesis.
Right.
The idea that every quantum measurement creates a split in the universe.
Leading to countless parallel realities.
Countless parallel realities.
Well, it's still a speculative idea.
Right.
It's fascinating to consider the implications.
Yeah, could we one day communicate with other versions of ourselves?
Right.
In these parallel universes?
Who knows?
Or tap into knowledge and resources from these alternate realities?
It's amazing to think about.
It really is.
Yeah.
Wow, those are some serious head scratchers.
They are.
It seems like with quantum computing, we're not just pushing the boundaries of technology.
We're pushing the boundaries of our understanding of reality itself.
It's a truly exciting time to be alive. Witnessing the birth of a technology that has the potential to reshape our world.
In profound ways.
In profound ways.
And while we're still in the early stages of this quantum revolution, I have a feeling we'll be looking back at this moment as the dawn of a new era.
I think that about wraps up our deep dive.
It does.
Into the world of quantum computing.
Yeah.
We covered a lot today.
We did.
Hopefully everyone listening learned something new.
I hope so.
And had their minds blown.
At least a little bit.
At least a little bit.
Yeah.
So keep those brains buzzing.
Stay curious.
Yeah, and stay curious.
Yeah.
Thanks for joining us on the deep dive.
Thanks for having me.